Okay, all right, let's do that. So for the recording, this is the VM forking and hypervisor-based fuzzing talk, round 2. Outline for this talk, I will talk a little bit intro and motivation for why we are doing this and what fuzzing is, and then we'll get straight into the nuts and bolts of VM forking, how it works on Zen. And then we will talk about 2 applications that we released as open source based on this Zen interface. One is kernel fuzzing with AFL, and the other one is malware fuzzing. And people are saying, I'm not getting any sound.
I can hear you.
Okay.
I think, yeah, I just continue.
Okay. And then hopefully we'll have some time for Q&A at the end. For those who don't know me, I'm senior security researcher at Intel since last year, but I've been working with Zen for a long time, especially on the introspection systems. And I mainly work on malware analysis and that type of stuff. So why fuzzing? No sound, no sound. Yeah, please rejoin, I guess. It's going to be the solution. In the meanwhile, I'm just going to keep going because I have a lot of material. Hopefully I can get through it. So fuzzing effectively is a time-tested method for software validation. It's very simple but very effective. We just throw a lot of input at the target code that you are exercising and try to see if it crashes under any type of input, which obviously should not happen under normal circumstances. For a more in-depth introduction to fuzzing, I highly recommend this talk from CCC. And usually the steps involved in setting up a fuzzer is writing a little harness for your target code that will effectively be utilized by the fuzzer to re-execute the same code over and over with different inputs. Generally speaking, this sounds easy to do, but the harder the code is to reach, the least likely it is for developers to actually set this harness up. So for example, fuzzing the kernel and any type of low-level code usually doesn't get done because it's just very hard to actually write an effective harness, especially for the operating system, where if you end up crashing it and it takes a minute or 2 to reboot your system, it's going to slow things down quite considerably, and it's kind of a pain to actually set that up. So there are kernel fuzzers available already that are open source. The most popular one is probably Syscolor for Linux, but it's also available to a bunch of operating systems. It requires support from the operating system since you are effectively fuzzing the system calls, and the operating system needs to cooperate. So there is a lot of legwork needed to actually get this working for custom operating systems or new types of operating systems. So this might not be necessarily the best tool for fuzzing the kernel, but for system calls, it's really good. KFL and Chocolate Milk are both hypervisor-based fuzzers and also are open source. KFL actually uses Intel PT. It's the processor trace feature for recording the coverage trace for the kernel. Chocolate Milk is a very new one. It's all written in Rust and it looks really awesome, but it's very experimental and might not be necessarily the easiest tool to use for your average developer. And that's really one of the motivation why we are making another one here. All of these tools that are available currently are very tightly coupled to their use case, and it's really not necessarily the best if you want to experiment with some new types of fuzzers or new types of binary analysis systems. We wanted to have something that's effective, but also easy to extend and customize, and furthermore, things building on interfaces that are upstream. So we upstreamed the VM forking feature to Zen to cut down on our development cost, make sure that this is rock solid, very low level, but we can actually build custom things on top. And of course, we have access to the VMI subsystem, which is a big bonus. We have access to all the hypervisor events, and we can really experiment with new use cases, which is, in our case, is malware fuzzing, actually. That was the use case that we were primarily after. Kernel fuzzing was something that was nice to get along the way. And as far as VM forking goes, I think in the fuzzing context, it's quite straightforward why we would need it. It's really slow to actually restore VMs from a snapshot. Even if you do it from a disk, it can be about 2 seconds. It's not ideal for fuzzers when you actually want to exercise the code thousands of times per second. And if it takes 2 seconds to reset, then that's going to take forever to actually find your results. And Zen, fortunately, had this subsystem sitting around for a long time now called memory sharing that we actually were able to use for this task without having to do a lot of legwork up front, since this was already there. It's been sitting around since 2009. Up till 2012, it had quite an active development, but then it dropped off. The maintainer left Zen. The code has had some bit rot over the years, but fantastically, it still mostly just works, which was awesome when we started building this VM forking system on top of it. Yeah, if you look at the Git log, you can actually see that it was by Citrix at the first. So the way memory sharing works is that both domain has to be subscribed effectively to participate in memory sharing. It's not something they can opt in. It's the privileged domain needs to subscribe them. And then the privileged domain can nominate a page for sharing, which actually takes the ownership away of that page from the domain that it was taken from and assigns it to this hidden domain called DOM-cow. Apparently, there are hidden domains on Zen that you don't actually see when you run XL list or something like that. These are domains that only the hypervisor knows about, and it's sort of a way for Zen to keep track of memory that don't actually belong to the hypervisor, but actually that don't belong to a particular domain either. So in memory sharing context, DOM-cow holds all those pages that are shared to multiple domains. In the original domain's memory page, the page is ripped out and replaced with a read-only page in the EPT. This is only available for Intel hardware, so this would be the EPT. And then multiple domains can map this page into their EPT and have access to it at the same time. And then whenever a domain actually falls with a write access, then that page gets deduplicated, copied into that particular domain that actually was accessing it with a write access. But if no domain is left mapping it as a shared only, read-only page, then it is released from DOM-cow. Memory management in Zen, I'm going to briefly touch upon. George actually is having a talk about this later in this Zen Developer Summit, so he's going to cover a lot of this, I believe, or I hope, and especially around reference counting. This was something that I spent quite a lot of time banging my head against the wall, trying to figure out who's holding reference to what page and why. So I'm really looking forward to that talk. But effectively, there is a reference counting system in Zen to keep track of which memory is safe to release. Since there are so many moving components in Zen, you can have the hypervisor, the domain itself, or the privileged domain, or subdomains mapping memory left and right. So you really need to make sure that you only release pages and reassign it to other domains when no one else is holding a reference to it. And this is obviously the case for memory sharing as well. But won't spend too much time on this. For VM forking, the base idea is that we create a P2M, so effectively an EPT that's empty. There are no pages mapped to it, and we just specify the parent domain for the fork, copy over the vCPU parameters from the parent domain, so the CPUs are all ready to go. And when you unpause this fork, it will obviously page fault because there is no memory mapped into it. And in the MMU handler, you just start to populate this page table on the fly. This is actually very similar to the alt P2M system, how that works in Zen that's already been present. So this has been heavily influenced by that design. And of course, if there's a write access, then you actually deduplicate the page right off the bat. You don't have to wait for the memory sharing to kick in. You can do that right there at the MMU handler. So I have some graphics here to show how this works. So you create a fork domain. It has the parent VM specified. You allocate some of the metadata necessary that contains things like the domain's ID and some of the C structures that are required for Zen to manage a domain. It's inserted into the linked list of domains and things like that. You copy over the vCPU context, but you actually have no memory attached to it. So when it executes, it starts to populate the page table of that domain and depending on the access type, different types of pages get plugged in. Some pages might be shared, some pages might get deduplicated. And then we have this operation called fork reset, which actually allows you to not have to refork a domain all the time. You actually can just recopy the vCPU context from the parent and throw away all the pages that had been deduplicated for that domain, which can actually save a lot of time during fuzzing. So some numbers to put it in context. A full fork, VM fork, is about 700 microseconds, so you can do 1300 per second. A fork reset, depending on how much memory got deduplicated and has to be cleaned up, it's about 100 microseconds, so upper limit is about 9,000 resets per second, which is pretty great, but it probably could be further streamlined, but 9,000 per second, that's pretty good start for fuzzing already. Of course, that's going to be an upper bound. We're never actually going to see that speed during fuzzing simply because we will be executing a lot of code in between. All right, so this is the first demo that we have here. Let me plug in the video. This actually is going to show us a full fork working on Zen. The screen might be a little, the text might be a little small, but effectively what I'm going to be showing is creating a VM fork with a fully functional Keynum instance running in the background, so the VM itself will look like and feel like just a regular domain, and in the background its memory is being populated by Zen on the fly. The way this interface has been designed is that you manually have to create the Keynum save file from the parent. This is because the design we were looking for was to fork the parent all the time, over and over. This was before we came up with the reset idea. So the idea here is that you have the parent already paused, you create this Keynum save file once using the QMP socket, and then you can just create forks from that paused parent all the time. You don't have to regenerate this Keynum save file over and over. And you can see that it was created fairly fast. It has a fully functional interface, so you can actually connect to this VM fork now over VNC. And you can see that it's using 33 megs of memory. Again, the text what's displaying is not important. I'm just logging in on the VNC screen and I'm going to start running some commands in the VM. You can see that as it's executing, it's still using very little memory, here though I already logged in. And you can actually do introspection on that fork, fully functional with VMI interface. So you can actually see the bash process showing up in there in the introspection process list example that actually just peeks into the memory of that VM. Start running top in the fork, and you can see that is popping up in the introspection system. So it has a fully functional introspection interface, which is what we will be using for the fuzzing itself. A little bit of more details about how this works. It's a little bit different than fork on Linux, namely because the parent domain actually has to remain paused. This was fine for our use case. If you actually want to implement a full domain split where both domains continue running, that can be done. It was out of scope for now for us, but effectively you would have to make some magic happen so that the pages that need to be that can be made shared have an extra copy laying around. So when those forks need to have them plugged into their page table, they are still around, and Zen didn't just free it up because no one was using them. Another feature that's pretty cool that I added, I wasn't really sure what will be the use case for it, but some users already found it handy, is that you can actually fork the forks. So you can actually have a chain of forks, all snapshotting effectively the execution state of that VM in different stages. Of course, only the edge forks will be able to execute. All the parent forks will be paused all up to the parent VM. But this is something to keep in mind while experimenting. That's pretty handy. And now the really interesting part is that you can actually create VM forks without Keynum at all. You don't populate any of the Zen store entries. You don't launch Keynum. You just run the fork with just CPU and memory assigned. And that means that only some parts of that VM is safe to execute. Obviously, any code that would try to interact with the devices that Keynum would be emulating in the back will not behave normally. But you know, usually when fuzzing, we are exercising very specific code locations, which is for this use case, this is perfect. We don't need Keynum at all. and we can actually block all the interrupts on the hypervisor side so that none of the interrupts will interfere with the execution of that VM. And then, of course, even in this state, without Keynum in the back, we have a fully functional VMI interface, which is what we will use for fuzzing. I have a demo here that actually shows pretty much the same thing, where we run the VMI process list on a fork. I will skip this demo just in the interest of time, but the video is available on YouTube and in the PowerPoint. Please feel free to watch it there. Another use case that we added was when we actually started using this system to start fuzzing kernel drivers that we are developing at Intel. And what we discovered was that it's really hard to fuzz kernel drivers that only initialize completely when they see a physical device available on the system. So we wanted to be able to just pass through the physical device using PCI pass-through to a VM and have the kernel driver fully initialized because it sees the device there, and then pick a location within that kernel driver in a fully initialized state and start fuzzing it in that point. And this works pretty great. We actually had a fuzzing setup for the integrated graphics driver, which we passed through using the IOMMU, and then we were actually able to fuzz the i915 kernel driver using the system, and it was fully functional and was actually driving an external 4K monitor. So this works pretty well and very handy for fuzzing kernel drivers in that state. And it's not limited to system calls. You can really fuzz any code part within that kernel driver, including DMA pages and everything. Really any code that runs within that VM is available for fuzzing. So yeah, it's really handy. So now putting it together with AFL, we can run multiple forks on multiple cores. Each can be independently utilized, so you can max out your hardware. And for AFL, the way we have the glue that actually makes AFL work with forks. Obviously, AFL itself is not going to be aware that it's fuzzing using a hypervisor, but what we ended up using is that in the VM, you just mark the code that you want to fuzz using a CPU ID harness. So there is this magic leaf that if the CPU ID instruction is executed with this magic leaf, then the user space tool using libvmi can actually tell it, okay, this is the start point in the code. I will pause the parent VM, and that's the point where we can actually start creating forks from and start fuzzing. And then the end code location is also marked by the CPU ID with the same leaf. And then for detecting crashes, you just breakpoint the kernel's crash handlers. So for example, in Linux, it would be oops and panic and page fault and things like that. You can breakpoint, and then those breakpoints will trap to the hypervisor as well, and they'll be interpreted by AFL as a crash detector. And I think I have a demo coming up here. Okay, so yeah, so this is the harness, how it looks like for what you would have to inject into your code to signal to the hypervisor that this is the beginning of the code that you want to fuzz. I have some push instructions here before the CPU ID instruction and then the pops after. This is because the CPU ID instruction clobbers those registers, and you just want to make sure that this harness is not going to interfere in any unintended way with the code that you are trying to fuzz. So you can really inject this harness call anywhere in your code, and it will not have any adverse effect with the surrounding code. This will just effectively, the CPU ID instruction is what will trap to the hypervisor, and then the VM will be paused right after, right here at the top. And here, of course, I have the harness before and the harness after the code that I want to fuzz, which will be this test function. All right. For coverage guidance, so AFL has this idea that it's better to fuzz code that hasn't been touched before. So it actually has this coverage guidance system built in that tracks if any code was discovered that wasn't exercised before, and will focus more on those paths that have been discovered during fuzzing. Obviously, we have to somehow implement this using the hypervisor because we can't recompile the kernel with that type of harnessing in place that AFL normally uses. AFL by default has this fork of CLang that does that coverage trace points during compilation. We're actually just going to use the hypervisor for this. What we do is we disassemble the code from the start and then breakpoint the next control flow instruction and single step over it using MTF, and then repeat as we follow the code along as it's executing. Obviously, this is going to add quite a lot of overhead because we disassemble the code as it's executing, and we are injecting breakpoints left and right. And of course, when we inject the breakpoint, it will do a full page deduplication. But in the long term, we actually are looking to replace this with Intel processor trace. Fortunately, the Polish cert guys are upstreaming that right now to Zen, so that's going to be available hopefully in the next release of Zen, and then we can replace this coverage guidance with Intel processor trace. So I have another video here for showing you how this looks like with AFL running. So again, sorry if the screen is too small, but I will just describe what we see as we go along. So I have the Debian VM running here. I will connect to its console using Excel console so that I can see the kernel messages as the kernel is printing stuff. I build this dummy kernel module that has the harness in place. I will actually show what the code inside that kernel module looks like. There are two dummy character arrays, dead beef and not beef, that one of them we will be actually fuzzing. Then I have the harness function. This is the same as we saw before. I have some dummy paths here just to test the coverage guidance that it works. And then in the test function, which is what we will fuzz, I have this Y pointer that just points to null. And if those two character arrays that we saw before, dead beef and not beef, are equal according to memcompare, we will trigger a null pointer deref oops. Obviously, if you execute this code normally, if you just load this into the kernel, nothing will happen. Obviously, those strings are never equal. But if we start fuzzing it, then the hope is that we will find the matching string that will trigger that path within the kernel module that has the bug, and we will see the kernel loops happening. So I start running with the first step is with the setup flag. And right now, on the left-hand side, the tool is waiting for that CPU ID instruction to happen again. So I just remove the kernel module, reload it, and right now the parent VM is paused right after that CPU ID instruction, at which point we can actually start the fuzzer. What we will do, actually, first I just remove the output folder that the fuzzer previously generated, and I will seed the fuzzer with a string that's close enough to the matching strings, just so that the fuzzer can find it fast enough for the fuzzer. So I start with the seed of not X beef and specify the address of where the first string is, and that string now will be replaced by the fuzzed input generated by AFL in the forks memory. And now AFL is running. It's already discovered all the paths and already found the crashing match. It's running about 200 iterations per second. This has been recorded about 2 months ago. In the meanwhile, we actually discovered that this can go way higher than that. Right now, this was running with 200 iterations per second because it was using hyperthreads. You disable hyperthreads or just make sure that the VM fork and the fuzzer are running on separate cores. It's actually going to be a lot faster. Here, the output actually shows that it found the not beef string as the matching string that caused the oops. So we can tell that this was actually finding the right, the crashing match for that memcompare to trigger the null deref oops. So yeah, so this is fairly effective and works pretty well. Obviously, we designed this for kernel fuzzing, but you can really fuzz any code that's runs within that VM, including user space as well, which turns out to be something that people were really interested in. So there are people already using this for fuzzing user space applications on Windows. We also use this for fuzzing other operating systems like Zephyr. So you can really, anything that boots within a Zen VM, you can use to fuzz this. This is just really the tool that we released is really just the demo for Linux. The code is released under MIT under the GitHub page. Feel free to fork this and target whatever else you want. Obviously, the upstream version is, we try to keep it as simple and streamlined as possible, but it's very configurable. Feel free to target whatever else you want, but we will try to keep features to the minimum on this upstream project because this is just the demo that people can use to build their own tools on top. All All right, with that, we can actually get to the point that we were really excited to talk about here. Is why we are building this whole thing is for fuzzing malware. The idea is that we want to exercise malware binaries in a way to trick them into executing their malicious payload without having to rely on anti-analysis tricks. One of the problems I see with a lot of the dynamic analysis systems right now is that they build in a lot of assumptions about how malware should execute or what kind of aspects of the execution environment they look for before they start executing, and it's not ideal. So we want to be able to fuzz malware binaries to gain confidence in the results that we get through large numbers of execution, and then automate and scale that. Obviously, there is a million problems with fuzzing malware that's very different than fuzzing any type of regular software, especially the ones that you have the source code for. For malware, obviously, we won't be able to hard code the harness into. We don't have source code. We don't have debug data. What if the malware actually places rootkits into the system, and then it's obfuscated? It has encrypted modules that get decrypted on the fly. How do you scale this? How do you contain this? What is even the input that you fuzz with malware? So there is a lot of questions here on how to approach this. But basically, what we were looking for is to get a system up and running that's very simple. Mainly because complexity, we see it as the bane of security. The more complex a system is, the more assumptions you build in. And then, of course, malware really loves to break those assumptions. So we need to keep this simple as much as possible, but also in a way that it just works, right? We don't want to have any customized harness, any custom thing targeting specific malware behavior. We just want this to work. And the way to do this is to look at what is the lowest layer that would be interpreted as an input to any type of program that runs on our CPU, and that would be memory. We've seen a lot of attacks that rely on memory corruption, and one of the offensive technique that was inspirational is row hammer. If you think about row hammer, that's effectively hardware fuzzing. You are hammering the RAM until it starts flipping bits. Obviously, we can't use the same technique for malware fuzzing because it's just too slow. We have way too many malware samples, and we don't want to rely on just the hardware glitching on us to get the results done. So what we were thinking is to virtualize row hammer and use that as the base for malware fuzzing. Turns out that this idea is not all that crazy. In 2016, Microsoft actually published this paper about this MicroExecution engine that they've been developing as part of their SAGE framework that they use internally. So this is not something that's open source. But what they effectively describe in this paper is very similar to what we had in mind, where they effectively propose a virtual machine where they can trap memory operations before they occur, allocate memory on the fly in order to perform those read and write operations, and then have a policy in place that can actually replace those values as the VM is executing with input values that are provided along the way that can be generated in various ways, randomly or using another test generation tool. Right? So this is fuzzing memory, effectively. This is very much what we had in mind as well. So it's pretty cool to see that other people have this idea as well, so that we are on the right track. And now we can build this system actually on top of Zen. And the idea is that we can trap the memory accesses that the VM is making using the EPP permissions. This is already wired into the introspection framework of Zen, so this is absolutely possible. And then every time an EPP permission trips into the hypervisor, we can fork the VM and then start fuzzing the memory content that just tripped the EPP fault, the EPP fault into the hypervisor, and start fuzzing that access in the forks with various values and see what happens, right? And we can do that for each memory access as the VM is executing. But doing this at scale for applications that would do thousands, hundreds of thousands of memory accesses is going to be very expensive, right? So randomly making, random binaries making access to memory, we have absolutely no idea about the purpose and the context of that memory access. We haven't encoded any assumptions about what it's doing. One option we could do is to just start mutating that memory content, but obviously mutating the memory content just randomly is going to be less effective. We don't really know. We might get lucky, but if there are thousands of memory accesses that you want to fuzz, this is going to take a really long time. So how to actually have a memory replacement policy or memory fuzzing policy that will be a little bit more effective. And here, what we had in mind was to reuse another offensive technique for a defensive purpose, and that is the replay attacks, which is obviously more targeted towards network applications, where you record packets flying over the network and replay them to the application out of context in hope that you will trip different behavior in the target. We can actually use the same idea for memory. And this is where memory replay was born. The idea is that we record the memory values as the VM is executing. We don't hardcode any addresses, any values. We just record all the memory accesses, read and write, as it flies through the system, and then replay them for every future access that's being made. And this is also a prototype that we released as open source. So this is up on Zenbit. And the system actually works really well. It's obviously very experimental. And the reason why we released this in this state as a proof of concept is in the hopes that the community will find this area of development and research of interest, and people will start experimenting with this system on various targets. And there is a lot of open issues that are still not resolved. But I really believe that this direction of thinking about how to analyze malware is going to be getting us out of the ditch of having anti-analysis tricks followed by anti-analysis tricks and that whole cat and mouse game. It would be way better to have something that's automated, scalable, no assumptions. You can just brute force, throw hardware at it, and you get better results because you can actually see if you get a false positive, you can actually have a trust that that false positive is not just because my environment didn't match what the malware was looking for, but you can say that, hey, I fuzzed this malware sample 1,000,000 times, effectively mutating its environment, and we haven't seen any malicious activity. Then you actually have a better idea that, okay, that binary might not actually really be malicious at all. So that's my talk. I have a lot of backup slides here. If anyone wants to get a little bit more into the nitty-gritty details of memory replay, but I think I'm at the 30-minute mark, which was what originally earmarked for me. So thank you. This went smoother this way without sharing my screen. So I'm really happy that we were able to rehost this talk, and I really hope that you learned something useful. And where do I send the bug fix to your CPU ID harness function? You can open an issue on GitHub, obviously, or you can ping me on Slack or send me an email. But both projects are open source, so you can absolutely ping me there. And really hoping that the community will find these tools useful and will improve security going forward. I understand we have time to till 11:30, so if there are questions, I'm happy to answer those. If not, then
15 minutes.
Yeah, if we have some more time, I might just going to start plowing through my backup slides, because I have about as many backup slides as I had slides so far. So up to you guys if you guys want to chat about this or want to see me give a shot to the rest of the slide deck. Giving the talk twice. Well, the first time I gave it to my kitchen, so it's nicer to actually see the feedback as I'm giving the talk. We're putting into OSS test to spot when upstream stuff breaks. This is all experimental, so this the VM forking feature will not be compiled by default in Zen. You have to enable the Zen expert config expert option and specifically have to opt into the compilation step. So I'm not sure if the OSS test system has that available or if that can be hooked in. But this is all considered very experimental, and we don't have any CI for it really. But if it could be hooked in, then that would be fantastic, obviously. I would start probably with the introspection system having OSS test, because we have the introspection system upstream for a long time as well without CI. So that might be the better target to start with.
Cool. Okay, let's talk about that in email or IRC.
Yeah, I think so too. That's probably worth.
It's probably just worth saying I do have some plans on how to sensibly get VMI into the CI loop with some XTF tests. I just need several months to come to actually make that work. What I was planning to do was to try and put some Python bindings in DOM0, so you have a split test, one of which is a microkernel doing specific actions, and the other half of which is checking for expected VMI trips. So you can check each individual VMI path and check that it gets correctly from the guest out to DOM0, and modifications made by the VMI side reflect properly inside the guest. So I do have some plans for how to do that. They just haven't materialized yet.
Sounds great. Let me know how I could help with that. Obviously, this would be really awesome, because right now the only CI we have is what we use with libVMI and my other binary analysis system, which obviously doesn't really do much validation on the low level. It just has some high-level validation that the things we expect to see when we trace system calls, for example, work or not. But XTF would be awesome. I'm really a big fan of XTF, obviously. So that would be really a fantastic resource to have for this.
Yes, please.
Yeah, I agree.
On the malware side, what do you constitute successful versus unsuccessful fuzzing? Is that it starts talking to its control server, or it suddenly manages to gain kernel level privilege? Because the thing is, you could fuzz for ages, but not really know whether it's done anything or not.
Exactly. Obviously, you will have to draw an upper bound of how many times you want to, trigger that malware. All of those bits you mentioned would be obviously things that we would consider as the malicious behavior that we would consider as a trap that would say that, okay, this binary is malicious, might warrant a manual reverse engineering effort on it or secondary analysis. Really depends on your context, right? Not necessarily everything is malicious in every context. So, if there is an application that opens up a socket, that might be malicious under, if it was a PDF. But if it was a application that's a TFTP server, for example, then it might not be malicious. So you have to consider, what is the context that you are fuzzing that malware in, so that you can define what do you consider malicious in that context. And that's going to be different for everyone. But the way I like to describe it is really just with the PDF example. If you have a PDF and you open it up, you should not see, registry entries being created. Obviously, no kernel module should get loaded as a result of that. Network socket most likely should not be open. And all of those things could be defined and monitored for using VMI. So if any of those happen, then you can tell that, okay, this is definitely not normal and should warrant a second look. As for how to draw an upper bound, that also depends on your security context. In some situations, you might want to hammer that binary for weeks and have millions of executions to see if you can trigger that malware or that binary to exhibit anything that you would consider malicious. In some other context, you might run it for an hour or two. It's really, again, about what do you consider your security context. There is obviously a lot of research here that still needs to be done to cut down on path explosion, which will inevitably happen when you start fuzzing things, because it will crash a lot. Obviously, when you start, for example, replacing memory values with other random memory values, you will be crashing that application a lot. And that's obviously going to be crashing different ways. So you have to filter all those out and make some decisions about what paths to follow, how to follow them. But you have to do that in a way without baking in assumptions about the malware, right? So that's the downside of it. So you have to find this balance between speed and just avoiding making your whole system more vulnerable for subversion. Are there any other questions? If I have 7 more minutes, I might just going to run through real quick with the example that I had here for the memory replay. It's not actually malware. I'm actually just have a sample here that shows you how to actually how it actually looks like when you fuzz a trivial memory context, a memory location for a very simple application. So I have this test application that I used with the memory replay test. This is very similar to the kernel module test that we saw with the AFL setup, where you have the 2 strings, the test function that just does a mem compare, and then I still have a harness here with the int 3s, and then I applied memory replay just to this trivial memory compare function. And I was expecting this to be as trivial as it gets, and it actually turns out to be really fun what happens here. If you actually look at that code and you disassemble, even with IDA, so even if you do manual reverse engineering of that very trivial code, you won't really spot anything. You see the two int 3s, you have the call, and within that call, it just calls the mem compare, loads the 2 strings into registers, called mem compare, and then based on what the result of the mem compare, whether it calls secret path or not, it will go back. So it's really a straightforward code. You wouldn't spot anything just by looking at this in the reverse engineer format either. And when we actually ran it through memory replay, we called it internally shredder. What you actually can see is, if you just run it by default, you can actually see that there is, for that small code segment, we can actually catch a lot of memory accesses. So just for that small code segment, we recorded 105 memory reads and 97 reads and writes. And if you actually look at the values, you see the 2 strings, deadbeef and notbeef, show up in there. But what the hell is all that other stuff? We started looking through whether secret path actually executed. And memory replay did actually trigger that secret path. Obviously, one of the mem compare values got replaced using memory replay in one of the forks. So secret path does get triggered. So we know that this actually is a functional fuzzing technique to trigger code paths that would not normally be hit. What's really interesting is that if we start looking at the logs and we check where that secret path actually started to execute, is down at fork 850, which is very interesting because the secret path actually executed 100 forks before. So we see that the new so this is where the string actually gets read, deadbeef, and then where the memory replay actually triggered the secret path was 100 memory accesses before even those strings were read by mem compare. So somehow we were able to corrupt the memory of that VM in a specific way to trigger that secret path even before the mem compare fetched the memory contents of those 2 strings into its execution state. So it's very strange. What the hell is going on here? This was a fun exercise that we did internally to try to figure out what might be happening here. This is an unknown memory location that got fetched. We don't really know what the original content was, that we actually replaced it there. But what we see from here in the logs is that the control flow instruction following that memory access actually fetches that memory, whatever we place into that memory location. So in this case, I just placed 1 into that memory location. This control flow instruction that follows actually fetches it into the instruction pointer, because then we see that new code actually executes at instruction 1. So obviously this must be a ret instruction that pops that address of the stack. And here, when we actually print out the value, it's printed backwards due to endianness, but this is actually a valid address within the application context that somehow triggers the secret paths execution in the application. So that means that this memory replay tool, that's really that simple. It was just effectively smash the stack of something, and that triggered the code execution of secret path. So we were like, okay, maybe something within memcompare actually has an extra call to another function, and we smash the stack of that so that everything just returned before memcompare even got to comparing the values. But this is not the case, because we specifically called memcompare with a length of 7, and these functions only get called if you have a length of 8. So that's not the case. So it wasn't something we smashed within memcompare, but something executes between calling the test function and the test function calling memcompare. And it turns out that this is the dynamic linker kicking in for a late binding. So if you just normally compile something on Linux, it actually doesn't load the addresses of where the memcompare function actually lives. It does it lazily when it first gets executed. So when it first tried to execute memcompare, it didn't find the address of it, so the linker had to look it up, and that's why we saw all those memory accesses. So there is secret code executing even before the secret path between here that this memory replay setup was actually able to catch and manipulate in a way that you can actually trigger this secret path even before those strings get fetched from memory. Obviously, if we recompile this test application with these linker flags so that the addresses are resolved at launch time instead of at runtime, then the memory access is dropped down to 6 reads and 3 writes. Just the values that are placed on the stack, those are the writes, and all the reads are just popping the values off the stack and reading those 2 strings. So yeah, so this was pretty cool of an exercise, and I think I'm out of time right now. I hope this was something that you found a fun exercise as well, walking through that. I certainly found it fascinating to find the dynamic linker, and that you can actually smash the stack of it to trigger secret paths that way. So that was unexpected. Thank you again for everyone for joining. I have more slides here, obviously. So feel free to download the slides, look through those, and feel free to ping me anytime you have questions about this. And thanks again.